Alright guys, let's open up to page 177. Make sure you have a calculator. Alright, so last week we were talking about how we can figure out graphically where the x-intercepts or roots are located from an equation. Okay, but what we were looking at are possibilities of where the roots are located, and we're going to be able to do that by hand, okay, without a calculator. But once we figure out those possibilities, we are going to use a calculator to eventually figure out which possibility or combination is the correct one. Okay, so we did a few examples on Friday. We're going to finish up with a few today, and then we're going to get into some equation writing to end the class. You're going to have to help me out though. Like, where did we leave off on Friday? I forget which example. We were on 3, or we need to do 3? We need to do 3. Okay, so let's go ahead and think about, if you want to read the directions at the top to kind of let it sink in a bit, we're going to figure out where are these roots located. How many are on the right side of the x-axis, aka the positive ones? How many are on the left side of the x-axis, aka the negative ones? How many are at the origin, aka a 0 x-intercept? And then how many are imaginary? Okay, those are the ones that we still need to account for, but we just can't see them on a graph. All right, so taking a look at 3, how might you want to tackle the positive x-intercepts first? What do we have to look at or analyze with that equation? Yeah, Rebecca? How many times the original equation, okay, the one you start with, changes sign. So go from one term to the next, and every time you move from a plus to a minus or a minus to a plus, you have to take that into consideration. So how many sign changes do you see in the original equation? Yeah. 2. Okay, can you label them for us?
It would be 2x minus 3x squared.
Okay.
And then negative 3x squared and 2x.
There you go. All right, so we have at most 2 positive x-intercepts. Okay, at most 2 of them on the right side of the graph. What's another possibility, though? How many could show up there? Yeah. 0. Okay, so these are the ones that you subtract 2 each time. So 2 minus 2 would give us 0. We're not going to subtract 2 again, because then we would have a negative number, and there's no way you can have a negative amount on the right-hand side. So we're just going to end at that 0. What about how many x-intercepts show up on the left-hand side of the x-axis, aka negative x-intercepts? What do we have to do for that one? Yeah.
Switch the signs of the odd for these.
Okay, so we're going to check out what I refer to as the negative equation. We're not making everything negative. I know that's probably not the right term for me to use, but we're going to plug in a negative x in for all the x's in the original. And Ashlyn mentioned how we kind of have a shortcut to help us simplify that. All of the odd-powered terms are going to switch sign. Okay, all the other ones, though, stay the same. So this would be a negative 2x cubed minus 3x squared minus 2x plus 1. So take a look at that equation and then look at your sign changes. Can we identify how many we have? Good, Marie? 1. Can you find it? Where were you looking? All right, so this one right here, the last one. Good. All right, so at most we have 1 x-intercept on the left-hand side. Are there any other possibilities? If we subtract 2, we're negative, right? Okay, that's kind of a no-no. Okay, so that's it for the negative ones. So we know we have at most 2 on the right, at most 1 on the left. How many might show up at the origin? What do you think for that one? Yeah, Marie? How'd you know? It's not being multiplied by x, right? If you take a look at the original equation, there's no way you can GCF or pull out a factor of x. So we'll say x is not a GCF. Maybe just as a little note, okay, to help you with that one. Looks good. All right, so let's go ahead and think about how many could be imaginary. Okay, x-intercepts are roots that should be there, we just can't see them. They're not graphable. where do we look in the equation to help us determine those ones? These are the tricky ones. We're going to take a look at these imaginaries a little bit more today. Let's think about this. How many total roots should we have? Yeah.
3.
How'd you know?
Because the
Highest degree is 3. Okay, so at most we should have 3 roots, okay, any combination of these or imaginary. On Friday, we were taking a look at how imaginary roots come from that quadratic formula, okay, and the quadratic formula has that plus or minus in it, okay. So as a result of the quadratic formula, imaginary roots, if you have any, are always going to show up in pairs. Remember how we discussed one's going to have the plus option, one's going to have the minus option? Okay, so they always show up in pairs, meaning that if you have any, there's going to be an even amount. Now, if we have at most 3, what are the even numbers that are less than 3? Yeah. You could have 2 or 0. There's no way you can have one imaginary number because it's missing its buddy or its pair. And there's no way you could have 3 because even though 2 of those 3 could be paired up, there would be one left over without its buddy. Okay, so imaginary numbers always show up in pairs. So out of all of these possibilities, we're going to create that little chart to help us list all the different combinations of what could happen. We'll eventually use the calculator to figure out which one is correct, but let's make a chart to list out all the possibilities. So if you go through these, maybe we have 2 positive x-intercepts. We'll always have 1 negative. We'll never have any at the origin. So what does that leave for our imaginary? We're either going to write down 2 or we're going to write down 0. Yeah.
0.
How'd you know?
Because since the plus and minus added to 3.
Mm-hmm. There we go. So you already listed 3 here. That was the total you mentioned that we should have before. So we kind of reached our quota right there, so we're not going to have any imaginary. So that's one possibility or combination that we have based off of these that we listed. Let's try another combination. Maybe we don't have any positive x-intercepts. We'll always have 1. We'll always have 1 negative. We'll always have none at the origin. So what does that leave for imaginary? You're either going to write a 2 or 0. Yeah, 2. Good, because we've got to add up to 3. Are there any other combos? I think that one's about it, right? We only have 2 options. Okay, so we know it's going to be one of the 2. Okay, we're not too sure, so we're going to go ahead and use our calculator to help us identify which of those 2 that we listed is the correct one. So we're going to go to y equals. You can clear out anything that's in the calculator, and we're going to type in the original problem. Okay, that's the one that we started with. That's the one that we're trying to figure out these x-intercepts for. Just so we're all on the same page, let's make sure our windows are the same. They don't really give us any idea as to what numbers to use, so you can make them whatever you want. Maybe we want to go in 5s in every direction and 10s in every direction. Do we have a preference? We can always go back and change it. Are we good with 5s? Okay. And go ahead and hit graph. Alright, so it looks like we cross once. Okay, notice how it's a multiplicity of 1. We cross once on the left-hand side, aka negative, but we don't have any on the positive and we don't have any at the origin. So based off that picture, we only have 1 negative x-intercept and 0 positive x-intercepts. Between our 2 options, which one's the correct one? Can you identify it? Yeah. The second one. So we'll put a little star by that one. Alright, for your notes, if you want to, you can go ahead and draw a picture of the graph just in case you reference these at some point. Okay, that's what the actual graph looks like. We doing okay? Coming back to us from Friday? Do you guys want to try one on your own? Go ahead and try 4. Let's see, how'd you do on 4? It looks like there's only one combination. Does that seem to work out for you guys? Okay, so if there's only one combination, then clearly that's going to be the one that is the right one. Okay, but if you wanted to, okay, just to double check, you could graph it. This is what your graph would have looked like, and notice how you have one negative x-intercept, you have one x-intercept at 0, and you have one x-intercept, sorry, that's positive. So far so good? Speak now, forever hold your peace. Do you guys want to try 5 on your own too? We're feeling brave this morning? Alright, go ahead, try 5. Let's see, for 5, can we get that table 2 options? All right, after you graphed it, which one was the correct one? Good, Ashlyn? The second one. Okay, so if you graph it, it looks kind of weird. I think it kind of looks like a parabola, perhaps. Okay, but even though it does look like a U shape, it still is quartic, right? So we have one x-intercept on the right-hand side, one x-intercept on the left-hand side, but with a total of 4, that means the 2 that we're kind of missing are imaginary. How do we do? Pretty good? Awesome. Okay, so imaginary roots, we can identify those based off of the total degree. Remember, they always show up in pairs because of that plus or minus. Okay, they always have that buddy. What we're going to do is talk about how these imaginary x-intercepts or roots affect an equation, okay, or how do they show up when we want to write an equation. So look at the top of the next page. We have suppose a polynomial has roots at -1. Okay, so this is a real root. We can graph it, right? You can put a point at -1. But the other root they're giving us is imaginary. Do you see that I in there? We cannot graph that one. So with that basic information, we're going to try to figure out what the equation of the graph would be with these particular x-intercepts. Okay, but let's just first talk about what type of function do we have here. Can you describe it? Do you think it's quadratic, cubic, quartic, quintic? Can we identify that degree? A little tricky. Good, Marie? Quadratic? Why? Okay, they give us 2 of them, right? They give us this x-intercept and they give us that x-intercept, which is 2, right? So you would think it's quadratic. That's a good guess. What's, yeah? Why? Why cubic? Imaginary numbers show up in pairs. Okay, so if they give us one imaginary number, we should be able to figure out what the pair one would be, right? Didn't we try that last week with the whole plus or minus? Okay, so even though they give us 2, the fact that they give us an imaginary means that there's another one in there paired up with this one. Okay, so we'll say cubic because there are 3 roots. X-intercepts, zeros, whatever words you want to say. Okay, let's go ahead and list those. So they give us the -1, they give us the 2i, but it's up to us to determine what is the buddy or the friend of the 2i imaginary root. Can you take a guess? Yeah. -2i. Notice how this one's a positive one, right? A plus 2i. So the other one would need that minus or negative option. So we have a -2i. Okay, so if these are the 3 roots, x-intercepts are zeros, let's go ahead and use those to write the equation for h of x. So if our root is -1, what would our factor look like? If another root is 2i, what would that factor look like? And if the other one is -2i, what would that factor look like? We're used to writing we're used to writing factors with real x-intercepts, but the imaginaries kind of work the same way too. So do you think we can fill those in? Good, Marie?
First will be x plus 1.
Yep.
And then x minus 2y.
Okay, so this one is a positive 2i. That means we'd have to have the opposite of that in here, just like we had the opposite of negative 1. Good, and then what's the last one? X plus 2i. Perfect. Do you see how that works the same way with the imaginaries? Okay, we're going to distribute all of this through. Okay, so this is in factored form. Notice how we said it's cubic, so they all have a power or multiplicity of 1. That's checking out. But let's go ahead and we're going to practice distributing all these through. So what I would personally do first is multiply the imaginaries together, because some interesting things are going to happen there, not to give too much away, but it's going to simplify to something nice for us. So if we're going to multiply these two together, we're going to go through a distribution or a FOIL process. We have x times x, which is x squared. Bless you. How would you want to write x times 2i? Order doesn't matter when you're multiplying. So if you have an x times a 2i, what are some ways you want to write it? Yeah.
2y.
You could do that. You could do 2ix, you could do 2xi, you could do i2x, you could do ix2, okay? All of those are being multiplied together, so order doesn't matter. If we go on to the next terms, we're going to have a negative 2i times an x, so any combination of those numbers and letters would be fine as well. Alright, now let's try the last one. We have a negative 2i times a positive 2i. What would that look like? Yeah.
Well, it would be negative. Well, yeah, negative 4i squared. Then I would be negative 1. Because if you multiply root negative 1 times root negative 1, it's just
You are totally on the right track. Is that what you're going to say too? Are we familiar with this concept? Have we seen I squared before? Do we remember that from Algebra 2? Okay, I'm going to revisit it. I wasn't expecting that you guys remembered or knew that, so that's great. But I'm just going to revisit just in case there's some of us in here that don't realize this. Okay, so I we use as the signifier of an imaginary number, okay, the symbol of an imaginary number. By definition, I is equal to the square root of negative 1. That's what we label it as. Now if we have I squared, that means we're squaring a square root of negative 1, but we know a square and a square root cancel each other out, so we're just left with negative 1. Okay, so what you can do is take this negative 1 value and substitute it in for that I squared spot. Okay, so we'll get there in a second. Do you notice anything else that might happen nicely for us after we distributed all those together? Yeah.
The 2ix and the 2ix cancel out.
They're going to cancel out. Good. Okay, so we're left with a negative 4 times a negative 1 if we do that substitution, which would change to a positive 4. Notice how if you multiply two imaginary factors together, you should no longer be left with that imaginary I symbol. Okay? Because these should technically cancel each other out by the buddy system. One's positive, one's negative. So when you simplify all those together, they'll eventually cancel each other out. And the I squared is the same value as a negative 1, which we can make that substitution with. So even though you are multiplying two imaginary factors together, you no longer have that I in there. Can we keep multiplying? Go ahead, Marie.
You can change x squared
Mm-hmm.
plus 4 to x plus 2 squared. So you know that it would have a multiplicity too.
Not quite. Okay, if this was x squared, it doesn't exactly work that way, because if you do x plus 2 squared, that means you have x plus 2 times another x plus 2. And if you go through the distribution process, you're going to end up with an x squared plus 4x plus 4. This one's doesn't have that middle term. Okay, but I understand where that came from. Okay, we're going to keep multiplying though. Okay, we already know what the individual factors look like. We're trying to get it into standard form, like no parentheses left. Okay, individual terms. So let's keep going through a distribution or a FOIL process. We can do x times x squared, which would be x to the third, and then x times 4, which would be a 4x, 1 times x squared, and then a 1 times a 4. So last thing you could possibly do is put everything in order, highest power to lowest power, and there's your equation. Okay, so you first start off in factored form just to get the general setup, but then you can expand it into standard form. We're doing okay? We're going to try another one. These imaginary roots can be tricky, but remember they always show up in pairs. So let's try the next one. Suppose a polynomial function has roots of x equals 1 with a multiplicity of 2 and this imaginary root. What type of function do we have? What do you think, Marie? Quartic, okay. Quartic because there are 4 roots. We should be able to label them. So Marie, how'd you know there were 4? Okay, so even though it's technically one x-intercept, it shows up twice. Okay, it's going to bounce off the graph if you had a picture of it, multiplicity of 2. So this one counts as 2 roots. And then what about the other 2? They give us one of them. We have a 3 plus I. 3 minus I. Yep, the buddy imaginary root. Good. Alright, so based off those roots and the multiplicities, because those are important too, let's go ahead and write our equation in factored form, and then we'll try to expand it. What might our first factor look like if you want to use the x-intercept of 1? Yeah. X minus 1 squared. Good. Multiplicity of 2 is that power. Alright, and this is when it gets good. What about the next one? What do you think, Marie? Are you trying to write this one in here? Right? Okay. So notice how this 3 is positive, right? Which means we would have to subtract it. Okay? So what we're going to do is we need to subtract this root. But notice how this root has 2 terms. So if you're subtracting the root, you're subtracting both terms. So if you subtract the 3, that's going to end up with a minus 3. But if you're also subtracting the I, you would need a minus I. A little tricky because now you have 2 things to take into consideration instead of just one number, like the real roots are. Alright, let's go ahead and try the next one. Notice how the 3 is positive, right? Yeah. Plus I. Good. So you have to subtract again both of the terms, minus 3. But if you're subtracting a negative I, it would change to a plus. Do we see that? A little different. Alright, let's go ahead and multiply everything together. So, let's think about, do you want to multiply the 2 imaginaries together first, or do you want to multiply the 2 reals together that we have first? Okay, we have a multiplicity of 2. Do we have a preference? We're going to have to do both anyway. Say it again. You want to do the imaginaries? Okay, so we'll come back to this first part. All right, now what's different about these imaginary roots is now we have 3 things listed in each factor, not just the 2 like we had in the last example. So this is going to be a lot of distribution. We just have to make sure we keep everything organized. Let's take the x from the first factor and distribute that in to everything. We can then take the -3 from that first imaginary factor and then distribute that in. You guys might have your own process on how you distribute things in, but you just got to make sure you multiply every term in. Okay, so let's see what we get in the end. X times x, -3x, plus ix, There's a lot of terms there. Do you notice anything nice that's going to happen? Remember, all the i's should eventually go away. So let's make sure that happens. Good, Marie?
You can cancel out ix with -ix.
All right, so that's gone and that's gone.
You can also cancel out -3i and plus
Okay.
and then -i squared.
Okay, so right here we have a negative times a -1. Looks good. I think all the i's went away, right? So we have an x squared, a -3x and another -3x would give us a -6x. And then we're left with a 9 minus a -1, which would change to a +1. So that would leave us with a 10. All the i's are gone, which is great. All right, let's now try to work with this real root that we had there, x minus 1 squared. This means you have to write it twice. Maybe I'll show that just so we're aware. And we're going to have to go through another distribution or FOIL process for those 2. So x squared minus x minus another x would give us a -2x, and then +1 on the end. So we multiplied the reals together and got this quadratic. We multiplied the imaginaries together and got this quadratic. Now we have to multiply those quadratics together to get our quartic, right? We need a power of 4 in the end with all the parentheses gone. So we have a lot more distribution to do. Again, you're going to bring everything in, however you guys feel comfortable with that. How are we doing with our distribution on steroids? A lot to do, right? Can we keep track of it? Keep it organized? All All right. Anything else you guys want to go over? We're done with our first section. So far, so good? All right, there's about 10 minutes left. Instead of starting the next section today, you can use the remaining period to maybe try some homework problems. You may need a calculator for some of them, like we've been doing in class. Okay, remember you can use the calculators while you're in here, but that website Desmos is a good one to use at home if you don't have a graphing calculator. Okay, you can go online and check out and see what the graphs look like too, to check your work. All right?